So yesterday we looked at how to do long division, and it works fine, but for certain types of problems, there is a better way to do division, and that's called synthetic. So we're going to look at that. And the other thing we're going to look at is how can we find rational zeros? There is a way to find everywhere that a graph can cross the x-axis if that number can be represented as a fraction. If it's not a fraction, if it's irrational, then that gets a little harder. But as long as it crosses somewhere that's a fraction, like 1.5, that's a fraction, 3 over 2. We could find them, no matter what, any degree polynomial. And I'm going to show you how to do it. So graphs can cross the x-axis at places that are fractions and places that are not. If it's a fraction, we call it rational. If it's not a fraction, it's irrational. I think we had an answer in the homework last night that said it was like the square root of 2.5. That's irrational. You cannot write the square root of 2.5 as a fraction. So the theorem that we're going to use, which I'm going to abbreviate as RRT from now on when I have to write it, is the rational root theorem. It's a theorem that gives you all the roots or all the zeros to a function as long as they are rational. And the idea is you would have a polynomial, and it ends up that there's only two things here that are really important. This polynomial could be like 8x cubed, and then the exponent would drop like 3x squared, then it would drop again, plus 4x, and then finally plus 7. That's like your constant. So that would just represent a polynomial. There's only two things there that are really important. First, the coefficient of the first term and the constant. Those are the two things that we're going to focus on. The stuff in the middle, we really don't need. What's that? Yeah, we don't need that. Now, what is important, I'm just going to summarize that. The constant can't be 0. We don't want that to happen. We don't want the constant at the end to be a 0. If it is a 0, then we're going to run into a problem. This technique I'm going to show you will not work. So if we have a rational 0, then that means you can write it as a fraction. Let's say the top of the fraction, just because we don't know the fraction, let's use variables. The top of the fraction will be p, the bottom of the fraction will be q. The p represents the numerator to your answer, q will represent the denominator. So if you can find a fraction that is a rational 0, then the number that's in the top has to be a factor of the constant. The number that's in the top has to be a factor that's in the constant. So for example, factors of 12. 1, 2, 3, 6, 12. Positive and negative. The number that's in the bottom part of your answer, if you're going to be able to find a rational 0, is a factor of the leading coefficient. A sub n is the leading coefficient. If a polynomial has a place that it crosses the x-axis at a fraction, the top number in that fraction has to be a factor of the constant. The bottom number in that fraction has to be a factor of the leading coefficient. What this theorem does for you, is, and you're going to see this in a minute, is it generates a list of possibilities. It's going to generate lots of possibilities, especially if the constant was a number like 24. Well, there's a lot of factors of 24. 1, 2, 3, 4, 6, 8, 12, 24. Positive and negative of every number I just said. So this theorem generates a list of possible roots. Not every single number generated with this theorem is a root. It's up to you to check the list of possibilities that are created and see which ones are and which ones are not roots. But at least it gives you a list of options to pick from. Otherwise, if you didn't have a list of options to pick from, and I gave you some random polynomial and said, without a graphing calculator, tell me where that crosses the x-axis. I guarantee you it will cross at a fraction. I don't know if it really does, but pretend I made up one that does. You wouldn't even know where to start. I mean, there's an infinite amount of fractions. This formula narrows down the fractions it could be.
Oh, I see.
That's what this theorem does. Gives you a starting point to look for roots. So let's take this problem and let's list out all, I'm going to add in the word possible rational roots. We're going to make a list of possible options. So just remember what P and Q are, and we're going to start by writing that down. P is the factors of the constant. What are all the factors of negative 6? 1,
3, and 6,
and the negatives. So positive or negative, 1, 2, 3, and 6. Q are all the factors of the leading coefficient. What are all the factors of that number?
1, plus minus 1.
Plus or minus 1, 2, 5, and 10. So if this graph, I'm not saying if, this is just a possible list of options. If it crosses the x-axis at a fraction, the number in the top of the fraction is one of those 8 values, and the number in the bottom of the fraction is one of those 8 values. So now we have a place to look. So let's list them all out. So to make the list, what you want to do is try to be just systematic with it. Start with a specific p-value in the numerator, and then list all the possible q values you could have for that p. So let's pretend that p is 1. We could have 1 over 1. We could have 1 over 2. We could have 1 over the 5. Or we could have 1 over the 10. Plus or minus on all of them.
Wait, why is that for P?
Because P is the factors of the leading coefficient, and Q is the factors of the constant. Sorry, other way around. P is the constant, Q is the leading coefficient.
Those look like one's the factors like you wrote for Q.
Well, the numbers in the top are the P, and the numbers in the bottom are all the different Q's.
Oh.
So what's the next P value that I could have? 2. Now, tell me all the different, I won't write them all yet, but tell me all the different denominators I could have with P being 2, and let's go through all the Q's. So I could have 2 over 1. I could have 2 over 2, but I already have that right here. So 2 over 2 would reduce to something I already have. So I'm going to skip 2 over 2. What would the next one be? 2 over the 5. And the last one?
2 over 10. Which is 1/5.
2 over the 10, but I already have that one as 1/5. So some of these are repeats. Now let's do all the ones with 3 in the top. I could have 3 over 1. I don't have that. Next one?
2.
3 over 2. Yep. 3 over 5. And 3 over 10. So those are all the possible options with a 3 in the top. And now let's do the 6. Just put boxes around these so you can see which ones were which. So now these are the options with 6 in the top. What would be my first one? 6 over 1, which we'll just call 6. Next one? 6 over 2, but we already have that as 3. So we don't have to do 6 over 2. What's the next one? 6 over 5. We already have 6 over 10 as 3/5. So if this graph is going to cross the x-axis at a fraction, it's one of these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's one of these 24 numbers. We've narrowed it down from an infinite amount of fractions to just 24. And they're all pretty close together. The biggest one is 6 and the smallest one is -6. So we don't have a large area to check. Between -6 and 6 is where all these numbers lie.
Wait, we didn't.
Okay. Any questions on how we generated this list of possible options? Now, unfortunately, it might be that this graph has no rational zeros, and none of those fractions would work. That might happen. But the graphing calculator is going to help us figure out which one of them work without having to plug them in. Because without a calculator, what you'd have to do now is check each possibility, plug it in for x, and see if you get 0 as an answer. Okay, that would take a while. So if we graph this and we look at it, we can eliminate most of these just by looking at the picture and saying, well, you know, is it close to 6 or is it not? If it doesn't look like it's near 6, we can cross 6 out. Right, and that's what we're going to do in this part. We're going to show that this graph ends up only crossing in one spot. So it does cross the x-axis, but we're going to show that where it crosses is irrational. So what that means, well, you'll think about what that means in a second. So let's graph that. So we've got 10 x to the 5th minus 3x squared plus x minus 6. I know zoom 6 is going to be fine because my answers are between -6 and 6. Okay, so without doing anything else, just looking at that picture, what does it look like it's pretty close to where it crosses? Okay, looks like it's close to 1. So let's go back and look at our list and cross out ones that don't make sense. So does it look like, let me put this over here so you can see it. Does it look like it's close to 0.5, 1/2? No, it doesn't even look close to that. Does it look like it's close to 1/5, 0.2? No. 1/10?
No.
2? No. 2/5? That's 0.4. 3? No. 1.5? Not really. 3/5? That's 0.6. Nah, I don't think it looks close to that. 3/10? No. Positive or -6? No, that's not even close. Now, 6/5? That's 1 1/5. That's like 1.2. I mean, I can tell it's not close really to 1.2. I mean, if you argued that it could be close to 6/5, I could kind of see it. You know, it might be close to it. I still don't think that's right. But if you listed that as a possible option, I would be okay with that. But I would definitely expect you to list 1 as a possible option. I think that's really the only one. So let's use the table on the calculator. Actually, no, we don't even need the table. Let's just calculate the 0. So pick a point to the left, pick a point right, and do your guess. So it says the 0 is 0.9505. is that a number in this list? So what does that mean about it? It has to be what? It has to be irrational. That proves it. Because if it was rational, it would be in this list. This is the list of rational options. This number is not in the list. So it has to be irrational. And that's what we want to write down. So, since the root is 0.9505, and that is not in the list of possible rational roots. Possible rational roots. It must be irrational. It has to be. Now, most problems, if they ask you to do the rational root theorem, you're going to get a result that's useful. You're not going to get something like this. But that's the explanation why this is irrational. So it does require you to be familiar with fractions a little bit. You have to kind of know that 0.9505 is not any of these fractions. Generally, the fractions you have to work with are pretty easy. So you should be able to change most of these fractions to decimals in your head. Okay. Any question on this one? Now this was a big one. That's a lot of possible rational roots. Usually you don't have that many factors for P and Q. You might have like 2 or 2 or 2 and 3, but 4 and 4 is a lot. That's a pretty big one. So we're going to come back to using the rational root theorem again. We will do another problem with it, but I want to combine it with something else we're going to learn, which is synthetic division. So synthetic division is a faster way to do long division. Sometimes. Long division works all of the time. You can divide whatever you want with long division. Synthetic division only works if you divide by something of the form x minus a number, which also implies you could do x plus a number. But if you have to divide by like x squared in the bottom, you can't use synthetic division, at least the way I'm going to teach it. So you'd have to go back to long division. So synthetic division, faster way to divide if you have a linear polynomial as your denominator. And just want to see where I put the example. Okay, so I think what I'll do is this. Now, there's going to be lots of ways to show different things, like to show something as a root, to show something as a zero. I'm going to show you one way that is going to be helpful. We want to prove that 3/2 is a root of this. Yes, one way to do it would be to fill in 3/2 for x and see if you get 0 for y. That would work. But you're going to have to do 3/2 cubed and then 3/2 squared and get common denominators. So you're going to be working with a lot of fractions, and that's not the easiest number to fill in. Now, if somebody said show 1 is a root of this polynomial, yeah, I just fill in 1. I can do 1 pretty quick in my head. But 3/2, I don't think that's the easiest number to work with. So instead of showing that 3/2 is a root, does anybody remember what else does that mean? If 3/2 is a root, then it means 3/2 is a 0. It means 3/2 is an x-intercept. But I'm thinking of the fourth way we mentioned it.
Oh.
What about a factor? If 3/2 is a root, then what would be a factor?
3/2 minus the constant.
Like what would go right here? Well, you'd have to have a factor here. Yeah.
X minus 3.
X minus 3 halves. What I'm going to do is show that x minus 3 halves is a factor. And that indirectly means that 3 halves is a 0. Now, how do I show something is a factor? What do we do? What does it mean if something is a factor of something else?
You divide it.
You divide it, keep going.
Cleanly, so without remainder.
Without a remainder. So all we really have to do in this problem is show that if you divide the original problem by x minus 3 halves, you're going to find that you get a remainder of 0. That proves that this is a factor. And that proves that 3 halves is a 0. So that's the idea. But we're going to do division and show the remainder is 0. Any question on that line of thinking? Okay, so we're answering the question indirectly by proving something else, which proves what they want us to show. So first step is we write down the number that comes after the minus sign. What's the number that comes after the minus sign in our factor? 3 halves. So we're going to put 3 halves on the outside of a symbol. And you don't write any letters when you do synthetic division. All we want to do is write down the coefficients of what we're dividing into, filling zeros in for missing terms. Am I missing any terms in what I'm going to divide into? No. So what would I write down for numbers?
2, 5, 1, and 3.
Yep. 2, -5, 1, and 3. I'm sorry, I copied that wrong. 2, -5, 1, and 3. That was the original problem. Okay, so that's your first step. Write down those coefficients. Step 2 is bring down the first coefficient. What's nice about this method in terms of the space it takes up on the paper, I can guarantee you all my work is going to fit in that box. It's not like long division where you're going to keep needing a bunch of space down and to the right. Everything's going to fit right there. So you bring down the first coefficient. The next thing you do is you multiply the number on the outside by the number you just brought down and put the answer right there. So we're going to multiply, what's 3 halves times 2? 3, and put the answer in that column. That's the second coefficient. Now, add those numbers up. The number I just wrote down and the second coefficient. What's -5 plus 3? -2. And keep repeating this until we're done, and then I'll explain what this bottom row means in terms of your answer. What's -3 halves times, or pi? 3 halves times -2? And 1 plus -3? -2. Remember, you're adding here, you're not subtracting like you did with long division. This is adding. And what's 3 halves times -2? And what's -3 plus 3? 0. So what do you think this 0 is? That's my remainder. I just got a remainder of 0, which proves that this is a factor, which proves 3 halves is a 0. We just proved it.
It's pretty nifty.
Yeah.
You put the step by step up there.
But what's this? So the last number is the remainder. I'm going to uncover that in a second. But what do you think this is? Yeah?
That would be like x squared, x, and then constant, right?
So these are my
Oh,
these are my coefficients.
Coefficients to your
Yeah.
x's.
Yes.
Those
These,
would be like the value above the division.
and actually, I should say it this way. These are my coefficients. This one is my constant. So constant, linear coefficient, squared coefficient. So in this case, my quotient is 2x squared minus 2x minus 2. I don't know if I can fit that here. This way. 2x squared minus 2x minus 2. That's how I would factor the original polynomial. X minus 3 halves. And notice the exponent in my quotient. It's now only a quadratic. I've taken a problem that had an exponent of 3 and reduced it to 2 factors, and one of them has an exponent of 2. Once we get something down to an exponent of 2, that's easy to work with. We can use quadratic formula to solve this factor. We can just solve this one very easily by just setting x minus 3 halves equal to 0 and add 3 halves to both sides. But when it had an exponent of 3, there was really no way to solve this if we had to. Using synthetic division takes the exponent down a number from a 3 to a 2. Now, how would you possibly come up with the fact that 3 halves could be a possible root? How would you come up with that fraction?
Choose possible.
Yeah. I gave you this time. But in some of the other problems, I'm going to say to do this, but you have to figure out this number. How do you figure it out? You use the rational root theorem. It will give you this number. Then you can do the process we just did.
Right.
If we had a problem like the first one and it doesn't have a rational root, then this whole method falls apart. You have to have something you can divide into and get a remainder of 0 for this to work. So I will give you something that works. All right. So let's use synthetic division to find the quotient and the remainder when you divide the 4th degree polynomial by x plus 3. First of all, does synthetic division apply?
Yes.
Yes. I wrote down that you had to divide by x minus a number.
But it's technically negative 3.
You could technically think of it as x minus, and then what comes after the minus is minus 3.
Wait, okay, did you get a final answer from the last one you just did?
Yes.
Alright, good. See that one.
So it said, write it in factored form. So I kind of ran out of space. This says 2x squared minus 2x minus 2. That's the factored form. I just didn't have enough space. So what number is going to go on the outside this time? Negative 3. And what about my coefficients? Right here.
3.
3, yep.
7. 0.
Mm-hmm.
1. Negative 11.
Negative 11. Now, when this number is not a fraction, this is a very fast process. It does not take long to do this. So if I go ahead and just do this at like normal speed for me, you bring down the 3. Negative 3 times 3 is 9. 9 plus...
X squared. Negative 3 times 3.
Negative 9. Yeah. Did you have a question?
Someone was just wondering whether
Oh, yeah. So the 0 comes from the x squared. We didn't have a 0. Lost my spot. So bring down the 3. Negative 3 times 3 is negative 9. Negative 9 plus 7 is negative 2. Negative 3 times negative 2 is 6. 0 plus 6 is 6. Negative 3 times 6 is negative 18. Plus 1 is negative 17. And negative 17 times negative 3 is 51. If I did that right. 51 minus 11 gives me a remainder of 40. So that's like full speed.
Sorry, did you run through the...
So we bring down the 3. We bring down, multiply, and add. Bring down the 3, multiply those two numbers, and then add the result. multiply these two numbers, negative 3 and negative 2, add the result. 6 times negative 3, add the result. And then negative 17 times negative 3 is 51, add the result. So what's my, this is kind of a separation between quotient and remainder. What's my quotient?
3x squared. I mean, I'm cubed, sorry.
3x cubed. Yep. Yep. You'll know if you start at the wrong exponent, because if you start at squared and then x and then the constant, then you're like, wait, what? So you'll have to go back and adjust your exponent. And what's the remainder? 40. So much faster than long division, but only works on certain types of problems. Oh, that's okay.
Is that 51? Oh, yeah.
Yeah, negative 3 times negative 7, that is 51. Negative 3 times negative 17, 51. Everything is right. Just copy that, don't listen to what I'm saying. So any questions on using synthetic SD? That stands for synthetic division. And as I mentioned earlier, you may see directions in the book that say use Horner's algorithm. That just means synthetic division. Okay. Show that 3 is not a 0. How could I show that 3 is not a 0? Kind of the same way we've been doing it. I know there is lots of ways to do it. You could graph it and use the calculator. But yeah.
Do the synthetic division same way we did last time and then get a remainder.
Right, we're hoping for a remainder this time. We're hoping we don't get 0. So instead of showing that 3 is not a 0, I'm going to show that x minus 3 is not a what? Fact. I'm going to show that x minus 3 does not divide into this evenly. That's what I'm going to show. Which will then mean that 3 is not a 0 of this polynomial. Okay, what goes on the outside? 3. And my coefficients?
2,
Negative 3. Go through the synthetic division. Bring down the 2. 3 times 2 is 6. 5 plus 6 is 11. 3 times 11 is 33. 33 minus 2 is 31. 3 times 31 is 93. And 93 minus 3 is your remainder is 90, which means it does not divide in evenly. So 3 is not a root. Yes?
Don't we have to put negative 3 in there? Because if it's x minus 3, it's actually x minus 3.
That's x plus 3.
So it's always x minus the root. In this case, 3 is the root, not negative 3.
Oh, okay.
So it's x minus the number that you're trying to prove or not prove is a root. So 3 is what we're working with. So fill 3 in after the minus sign. If it said this, now you're trying to show that negative 3 is not a root. So it would be x minus minus 3. And then you'd have a minus over there. Yep.
Would you be able to write that in the factor form?
This?
What we got.
I can write this out, but I can't factor this because I didn't get something that went into it evenly. So this result is useless for factoring. But I can write out.
Can you write it the same way that you're feeling?
Yeah. So this would be your quotient, and this would be your remainder. But again, completely useless to do anything with in this problem. Doesn't help me at all. Questions on that? Okay, so in general, how do we find roots? Like, how do we actually figure out the root from scratch if they don't tell us? They just give us a problem and say solve. 3 different things we want to keep in mind. One is rational root theorem. That will give you a list of possibilities. The graphing calculator will help you narrow down that list. And then once you find a candidate that you think is a root, divide through by it using synthetic division. We don't want to waste time trying every single possibility with synthetic division. It's going to take forever. Think of that first problem. You would have done 24 synthetic divisions and realized none of them worked. Use the calculator to eliminate some for you. Okay, so it says find all rational zeros of x cubed minus 3x minus 2. That's a cubic. We don't know a formula for solving cubics. The only way we're going to be able to deal with this is if we can turn the cubic into a quadratic using synthetic division. So we need to find something to divide by that will give us 0. Let's use the rational root theorem to make a list of options. What are my values for p in this case? Those are factors of the constant.
Is there a symbol for rational and all this? Oh, plus was like a short A.
Not that I know of. No. Yep.
Plus or minus
1.
And plus minus.
Plus or minus 2. What are my options for q?
Plus or minus 1.
Plus or minus 1. So there are not that many rational root possibilities in this problem. How could I make a list of possible rational roots? What would they include?
Plus or minus over.
Plus or minus 1 over 1. Yeah. 2 over 1. That's it. That's 1 over 1, 2 over 1. So if this graph crosses the x-axis at a nice spot, it's either going to be 1, -1, 2, or -2. That's pretty quick to figure out which one of these might work. Let's graph it and narrow that list down. Even doing 4 synthetic divisions, I don't want to guess. I can still do it faster if I use the calculator to help me. So x cubed minus 3x minus 2. So, out of those 4 numbers, which ones look reasonable?
-1 and 2.
I would say -1 and 2 look reasonable. Which one you pick doesn't matter. You're going to be able to do the problem either way. So let's pick -1. Let's try to prove that -1 is a root. So what we're going to do is divide through synthetically by -1 and hope that I get a remainder of 0. So on the outside I would have 1, 0, -3, -2. And let's go through the synthetic division. Bring down the 1. What's -1 times 1?
-1.
Add those up. -1 times -1. Add those up. -1 times -2. 2. Add those up. 0. We just proved that -1 is a root. So let's start making a list of answers. So the roots in this problem are -1. And now we basically have this. This cubic factors as x plus 1 times something else. I know the root for this is -1. I need the roots for the question mark. Well, what is the question mark? It's the quotient. That's the other piece that this would factor into. X plus 1 times x squared minus x minus 2. That's the other factor, the quotient. So now this problem is about finding the zeros of that quotient. X squared minus x minus 2. How does that factor? We don't need to use synthetic division and rational root theorem again because we've gotten it down to a quadratic. From here, we can do what we know how to do.
Plus 1
X minus 2. Let's check it. X squared minus 2 plus 1 is minus 1, and 1 times negative 2 is negative 2. So what would make this 0? Negative 1 again. And what would make this 0? 2. So the answers we get are negative 1, another negative 1, but we don't have to write it twice, and 2. And if we look at the picture, that confirms it touches the x-axis twice. Negative 1, if you want to know what this is technically called, it's called a repeated root. When you see a cubic come up, touch the graph, and bounce away from it like that, that's usually an indication that this is going to be a repeated root. And that's what we got, negative 1, and we got another negative 1. If you had done synthetic division with the 2 to start, you would have been fine. You just would have ended up with a little bit different quadratic, but it would have factored and given you the same answers. Any question on that? Okay, let's find this. Find all rational zeros of this one. We can't just guess. You need a place to start. So let's start with rational root theorem. What are my p-values?
Negative 1 and 1.
Yep, not that many. What are my q-values? Yep.
Negative 2 and 2, negative 3 and 3, negative 1 and 1, and negative 6.
Yep. So plus or minus 1, 2, 3, 6. So all my possible rational roots. So list of possible rational roots include plus or minus 1, 1 over 2, 1 over 3, 1 over 6. Any question on those possibilities? Okay, let's use the calculator and see what it is. 6x, was that cubed? 6x cubed?
Yeah.
It must have been, yeah. Minus 5x squared plus 3x minus 1. And we only need to look between negative 1 and 1. Our answers are going to be in there. So standard window is way more than you need, but it's okay. Okay. What, out of our list, which ones look reasonable?
1/2,
Maybe one there. I would definitely say 1/2. So what I'm going to do quick to check it is press trace. 25. Yes. 1/2 is a root. So let's write that down. So 1/2 is a root. So we're going to divide through by it synthetically. And that's going to turn this cubic into a quadratic, which we can then factor to find the other roots. If there are other roots. But I can tell by looking at this picture, I can tell some. So 1/2 is a root, and we've got 6, negative 5, 3, negative 1. And what do we already know the remainder is going to be? Yeah. 6, negative 5, that's why I was double checking it. Positive 3, negative 1. So let's hope that that happens. What's half of 6? And negative 5 plus 3? Half of negative 2? 3 plus negative 1? And half of 2? Add them up. Perfect. All right, so we get, we've proved that 1/2 is a root. And if I look at what's left, think of this in the quadratic as A, B, and C. Let's just check something real quick. What's B squared in this case?
4.
B squared minus 4 times what's A? And what's C? 4 times 6 is 24, and 24 times 2 is 48. 4 minus 48 is negative 44. That's the discriminant, and it came out negative. So what does that mean about the other answers to this quadratic? There's only one real root. If the discriminant comes out negative, remember this is the part under the square root, you can't do the square root of negative 44. So there's no reason to even try to factor this problem. It won't work. There is only one answer. That's really 1/2. Okay, so we did one where we got to this step and then it factored, and we got a little more. Then we did one where we got to this step and it's imaginary. Okay, you cannot factor it. And the quick way to check that is with the discriminant, b squared minus 4ac.
Because it's negative, that means it can only have one root.
One real root, yes. Because we just, in the quadratic formula, we just figured out this. I know there's some other stuff, but I was just interested in what's under the root, and it came out negative. That's no good. Any question on that? Okay. There's that one. Yeah, I'm not doing that. I'm not doing that. And that. So yeah, this is the last one. Okay, find all real roots and classify them as rational or irrational. Okay. What would be my first step? Yep, rational root theorem. Find the P's and Q's. What's P in this case?
Or, oh, one, plus or minus 1, plus or minus 2.
Not that bad. Plus or minus 1, plus or minus 2. What's Q?
Plus or minus 3, plus or minus 3.
Okay, not bad. Way less than the very first one I gave you. So what would be the possible rational roots? 1, yep. What else? 1/3. Okay. 2. And 2/3. Okay, so only 8 numbers to check, all between 1 and -1. Standard window will show us which ones are reasonable very quick. So 3x cubed minus 8x squared plus x plus 2. I could zoom in a little. I don't think I'll need to unless it's between 1/3 and 2/3. That could be hard to see. Yeah, maybe not. Okay, so out of those possibilities, which ones look reasonable?
-1/3, positive 2.
All right, let's try positive 2/3. Hit trace. Type in 2/3. 2/3 is a root. That's all we need. Let's try -1/3 and see if that one works. Trace -1/3. No. -1/3 was not a root. It looked close, and I would definitely, if you put that in a list of things to consider, I would agree with you. But it doesn't work.
So
It's only
positive 2.
it's positive 2/3. Well, it's definitely not plus or minus 2. I mean, we're not, no question there. It's not plus or minus 1. It's definitely not plus 1/3. We know it's not minus 1/3 because we checked. It's not minus 2/3. So the only possible option that was left was positive 2/3. All right, and we confirmed it. All right, let's write that down. So roots. These are going to be my answers. 2/3. And is that rational or irrational?
That's rational.
That's rational.
It's pretty rational.
Yep. So what does that mean about these other places where it crosses? It has to be two of them, and they have to be irrational. Now I need to know what they are. There will be two of them. So what are we going to divide through by synthetically? Divide through by your root. What are my coefficients? 3, -8, 1, 2. A little annoying with fraction, but we can work with it. What's 2/3 times 3? 2. -8 plus 2? -6. Now here's how we can do this one quick. What's 2 times -6? -12 divided by 3. -4 plus 1 is -3. What's -3 times 2? Yeah, -6 and then divide by 3. Which is -2. There's the different ways you can think about that one.
Right.
But we get a remainder of 0, so we already knew that. Now, focus on finding the zeros of that, which is a degree 2. 3x squared minus 6x minus 3. What could you divide everything by? Yeah, you divide everything by 3. Is it going to be factorable? You should already know the answer to that.
Oh, yeah, no.
Well, these answers are going to be what?
Irrational.
So then it's not factorable.
Yes.
So we're not going to be able to factor it. So 1, -2, -1. Okay, what's b squared? I'm sorry, what's negative b? Plus or minus. Now, what's b squared? Minus 4 times what? 1 times -2. Sorry, -1. 4ac over 2a, which is 2. So 2 plus or minus. Well, minus a minus is going to become a plus. So that's the square root of 4 times 1 is 4, times 1 is 4, plus 4 is 8. And what is the square root of 8?
Square root of 8, 2 squared.
2 square root of 2. And what cancels everywhere that's not under a root? You can cancel a 2 from everywhere that's not under a root. So you end up with 1 plus or minus square root of 2. 1 plus or minus square root of 2. Those are the irrational ones. Let's do second calc 0, and let's just quickly check the one on the right. I get 2.414. Let's see what 1 plus the square root of 2 is. 1 plus the square root of 2, 2.414, same thing. So calculating the 0 on the calculator will not give you this. It will give you 2.414. If they want it exact, you got to do quadratic formula. Okay, but that's the answer. 3 roots. Yeah.
Oh, can I just see the beginning of how you found the irrational?
Yeah. So we listed the p's and the q's.
Or like how you found 1 plus or minus square root.
Oh, for the quadratic formula?
Oh.
That came from this.
Okay.
Wait, why did in the one before we only use b squared minus 4ac instead of using the whole equation?
Because in the other one, I already knew it wasn't going to work. So I just wanted to show you quickly that it wasn't.
Oh, okay.
And remember when we graphed it, it only crossed the axis one time? That's how I knew the other answers weren't going to be there. They would be imaginary. But this time it crossed 3 times, so I knew it would work.
I see.
Okay, so that's almost done. Almost. I have to fix it. So we are. So we're not going to do those 2, and then I think everything else is okay. So I think it's like 10 questions, 10 or 11 questions. Okay, so tomorrow we'll look at that, and then we'll look at section 3.5, which I think starts to get into doing it with imaginaries. So now we haven't been talking about the imaginaries. We will tomorrow.